Welcome to the dynamic learning hub of ExcelR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Doubly, Silicon India and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. ExcelR. We don't just train, we build careers.
Yes, so the collaboration with ExcelR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if ExcelR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with ExcelR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank ExcelR for being a part of it.
Good evening, all. I hope I'm audible to everyone.
Hello, good evening.
Yeah, good evening, sir. You can start the session.
Okay, fine. Thank you. Okay, good evening, guys. Hope you are doing great. Yeah. How are you all? Am I audible? Good evening, everyone. Okay, fine. Thank you. Yeah. So, what we discussed yesterday? Just a quick recap. Good. Recursion in Java. If you remember recursion, I hope that was clear. Recursion, na? I guess I have given an example on recursion as well. If you remember recursion, that onion peeling, or I can say that Russian dolls. And two important things in recursion. One is base case, another one is recursive calls. Right? With the help of that, I guess we discussed recursion in detail. Later we took examples of recursion, be it Fibonacci series or factorial of a number. Then based on that, we did that recursion with the help of dynamic programming by the concept of memorization. Because we have a naive Fibonacci or naive recursion. For that, it is not that efficient. To remember, try to recap things like this, right? If you remember that naive recursion or naive Fibonacci, that was not that efficient because can anyone give the reason why that naive Fibonacci was not efficient? Yes, we discussed it yesterday, right? Why was not that efficient? Okay, I guess we discussed it. You should answer. Why that was not efficient? Anyone? Then we discussed recursion with the help of dynamic programming. Good. Because it was calculating the same function, or I can say it was calculating the same value multiple times. Like suppose if you have to find a Fibonacci of, I can say low 11th number. So it will go to 10th and 9th. Then 10th would be 9th plus 8th. 9th would be 8th plus 7th. So it will calculate same value multiple times. So for that reason, it becomes less efficient. And the alternative to it was using memorization with the help of dynamic programming, top-down dynamic programming or bottom-up dynamic programming. So with the help of that dynamic programming, what we are doing? We are calculating the value only once. Later, then we are giving that or we are storing that in a data structure. Right? So once it has been calculated, next time whenever we are in need of that value, like suppose if it is Fibonacci of 7, so we don't have to calculate it. It has been calculated already. So now it has been stored somewhere in the storage, in the memory stack. So we'll go to that location, pick the value, and that's it. So with this, the efficiency of the algorithm, the Fibonacci is increasing. So it goes to of the order of, I guess, n. Otherwise, it was of exponential. I'm not sure the screen it. Otherwise, it was of the order of exponentiation. So we discussed it. Then recursive, there are two parts in recursion that we discussed yesterday. We have base case and we have the recursive call, and you know it well. What is the base case? For every algorithm, we have a base case. Right? Whenever you are solving any recursive problem, there is a base case. For a factorial, the base case is either 0 factorial 1 or 1 factorial 1. For a Fibonacci, the base case is first two terms, 0 and 1. Similarly, for other problems, we have a base case. Or we call that as precondition, base condition. Right? Okay, so after that, what we did? After that, we directly went to linked list. Right? Then we discuss about linked list. We give the example of linked list, that train I told you, kind of an example. We have multiple coaches, they are connected to one another. Means coach contains data, and at the end of the coach there is a link, there is a connector to the second coach, means coach after that. Then that second coach also contains data, and there, if there is another coach connected to it, there would be a connector between the second coach and the third coach, means a kind of a link or a reference. So in this way we have got linked list. Then we discuss about something singly linked list, doubly linked list, and not in detail, but in singly linked list we discuss it in detail. I guess we did the operation of insertion in the singly linked list, right? At the beginning, at any place, and at the end. We did the algorithm for that as well. And also we discussed about this. How do we create this node? The node creation. This. How do we create it? Just a minute, I don't know what got printed. So we discussed like this. How do we create a node? And I know it is like very simple now, and you might be getting it. Simply you have to create a node, and what is the data? Then the next part of that means the reference part. Then we have to create a constructor. In that constructor, we are simply passing data. Then this dot data that we discussed yesterday and everything about it. Okay. Then we discuss these two algorithms as well. Insert at the end, insert at the after some node. And this was the program. And today what we will see, we will discuss this operation. Deleting a node in a linked list. In a singly linked list, keep it in mind. See, if we see this algorithm, it is simple. It is not that much difficult. If we see, we have an algorithm, or I can say we have a problem of like this. It is a linked list, and we want a node to get deleted at any place, right? So for that, I have an integer key to be deleted. Means any node, I want that integer key to get deleted from the linked list, and output would be, it would be a list with node removed. Means if this was the original list, I then want the next list with this node removed, right? Then these are the steps. Let us explain the steps. Okay, the very first step is, if we see, it is set temp is equivalent to head. What does this mean, setting temp is equivalent to head? Can anyone? It is simple. We will initialize a pointer temp. This is a pointer. Let me clear the drawings first. We will initialize a pointer temp. This pointer, this temp. We will initialize it to the head of the list. Means the pointer is, this pointer will be used to traverse the list, this temp pointer, and we are initializing this to point to the head of the list. Means this temp would be a pointer, right? And it will point to the head of the list by this statement, set temp is equivalent to head. And with the help of this pointer, what will be doing? It will be used to traverse the list. Means this temp pointer will be used to traverse the list. And I have set this temp pointer as what? As head. Right? Then there is a next statement. Next statement is this. Set previous is equal to null. What does this mean, set previous is equal to null? it will initialize the second pointer previous. See, I have initialized 2 pointers. One is this head, another one is this previous. So it will initialize the second pointer. First was like I was initializing head, this not temp pointer, and now I will be initializing previous pointer, and this previous pointer I am initializing to null. And with the help of this previous pointer, I will keep track of the previous node during the traversal. Means I have to keep track of the previous node during the traversal. So I have created what? 2 pointers. One is temp, another one is previous. This temp is initialized to head, and it point to the head of the list. And the second pointer previous, it is initialized to null to keep track of the previous node during traversal. See, it starts as null, this previous, because before the head there is nothing. For example, if I have the linked list, so I am setting this temp pointer to point to the head of list. Like suppose if it is temp, I am starting with this pointer and it will point to the head of the list. And with the help of this temp pointer, I will traverse the whole list. First this, then this by incrementing it. Then I am setting a second pointer previous, right? And this previous is also set to null. It will be used to keep track of the previous node. And it starts as null because before the head there is nothing. For example, we have got next, right? But we have got previous as well. But when previous is equal to null, it means before this head there is nothing, for which I have initialized the temp, means there is nothing. Before head there is nothing. This is simply what this previous is equal to null means, this statement. I hope these two are clear. Yes or no? Yes. Is it fine? Okay, great. So I have only used two variables till now, temp and previous. Temp is simply used for what? Yeah, as a temporary pointer that is used to look for each node, and it will start from the head. Temp is equivalent to head. Then I have used another pointer previous, and it will keep track of the other nodes when we go forward. And we have set it as null because there is no previous node before the head. So these two statements designate this. Then we have, see, if temp is not equal to null and temp dot data, yes, temp dot data is equivalent to key. So what does this mean? Yeah, anyone? Actually, this is checking two things. Traversing, good. See, actually, let me choose a different color now because it is checking, actually, this thing is actually checking two things. Right? First thing is that the list is not empty. Temp is not equal to null. Means if temp is not equal to null, what does this mean? This means this temp is pointing to something. So the list is not empty. Right? Then the head node contains C. Temp dot data is equivalent to key. So it means this head node, it contains the key, whatever is the value, means whatever key it is. If it is the data which is to be removed, so it means the list is not empty. So what does this mean? If both these things are true, so what does this mean? It simply means that this is the node which is to be deleted. Because I have found the key over here, because it is the key that I have to delete. So I have just checked temp is not equal to null, means this list is not empty, and temp dot data is equivalent to key, means the key for which I am searching. So I have to delete that. So I am returning, right? Then there is one more part of the program. Let us check this part. Let me clear the drawings for this. Here. So for this portion, I am just checking list is not empty, and the key which I am searching for, that is in the temp dot data. So what I will do, there is a next statement. But set head is equivalent to temp dot next. So what does this mean? It will simply update what? This. Again, I will be removing. This set head is equivalent to temp dot next. What does it will update? It will update head to skip over the current head node, means it will simply update the head, right? Simply, it will simply update the head by temp dot next, because see, temp is not equal to null, so the list is not empty, and temp dot data is key, means the key which I want to delete. So when I am deleting like this key, so what should I now do? I have to update this head now, the head to which was not pointing to null. So that head would be temp dot next, means whatever was pointing to it will point now to this. So this is actually what I am doing. It will simply remove the what node, or I can say delete the head node by removing reference to it. When I am writing this, set temp head is equivalent to temp dot next. So it will update the head, and it will update the head by deleting the head node, simply by removing the reference to it. Fine. And then we will go return. Simply we have found that key which the node or the key which I have to delete, and I am returning. Now while temp is not equal to null, right, the list is not empty, and temp dot data is not equal to key, means this, the key which I am going to delete, the node which I am going to delete, it is not present in the temp node. So what should I do? Yes, can anyone? What will happen with this? Let me clear the drawings. This part now. Only like this part. Temp dot data is not equal to key. So what does this mean? It will simply traverse the list until it will reach the end of the list. Sorry. So when the list is not empty and it is searching for this, so until till what point it will search? It will search till the end of the list. Means whenever the end of the list is reached, it will stop. Means the node is null, end of the list, or I can say the node with data is equivalent to key is found. Two things are there. The list is not empty, and temp dot data is not equal to key. So what does this mean? It will start first node, then second node, then third node, till all the nodes are searched, means till it will not reach null, or till the key value is found. So two things are there, right? So after that, what it will do? It will simply set temp is equivalent to previous. So what does this temp is equivalent to previous mean? It will simply, I can say like now, store the current node in the previous. Means whatever is present in the current node, it will give that to previous node. Because it has to remove the node, it has to throw it away. Right? So simply it will store the current node in the previous before going to next. Under later to then send temp is equivalent to temp dot next. So what does this mean? It will simply move the pointer to the next node. This temp is equivalent to temp dot next. With this, the pointer will be moved to the next position. Means first this, then this, then this. If temp is equivalent to null, return. Means until it will move the temp to next position, next position, next position, till temp. When temp reaches to null, it will return. Means when temp reaches to null, it means we are at the end of the list. So at that time, it will return and it will simply set temp dot next. The previous dot next is equivalent to temp dot next. So it means what? It means it will update the next pointer of the previous node. Means this removes the target node from the list by bypassing. Means whatever was the target node which we want to delete, so it will remove that. So with this, we are actually deleting the node. Simple. Right? For example, let us take an example to get it more clear. Let us take a linked list like this. For example, let me make use of annotation. I have a node or a linked list. Like suppose I have head, then head is pointing to like suppose node 1, which is pointing to node 2, I can say, which is then pointing to node, or I can say not, I will write data inside, then don't get confused. That is why I'm changing the value. And it represents actually data, because we know this node has till now singly linked list, two parts, node, this link part and the data part. So I'm representing the data over here. Then it will be like node, for example, 7. Here it is link. Then it will be what? Can anyone guess if it is the last node, what would be the value? What it will be? If it is the last node, what is the value? Good, it is null. So this is the linked list, right? Okay. Let us move it a bit here. Okay. Now let us say we want to delete node 5. I can write like this. Delete, not node, I will say like the data. Data, delete, I can say delete node containing 5. So what will I do? This was the initial. So after deleting node, what could be the shape of this list? Yes, it would be simply without this. Let me okay, let me remove it. So it should be without this 5. I will not completely remove that. So it should be like 3 should be now linked to like this. It should now link to 7. This should be the final list, right? So in other words, I can say I have to remove this 5 from the linked list. Okay. So this is how do we do it, right? Are you getting it or not? So simply what we did, if we see, if I go to the algorithm right here, this was the input and this is the final output. So what I do, initially I will set temp is equivalent to head. So here temp will point to what? In the example above, if I will explain this, let me explain the example. So here, what will happen? It will simply, if I write this, na temp is equivalent to head, the first part of the program, this. So what does this designate as per the program? This will simply say that temp will point to 1. Write this. Temp points to this. Right? So when I said previous is equal to null in the as per the algorithm here. So that means, what does that mean? That simply means previous is null. Right? So when I say temp is equal to head, it means temp points to 1 here. And when I say previous is equal to null, it means previous is null. Whatever was the previous, so it is null. Right? See, now I am checking. Is temp not equal to null? What is the temp over here? The temp is pointing to 1, so it is 1. So it means that temp is not equal to null. Over here, na, this statement, temp is not equal to null. If you check over here, temp is not equal to null. So in this case, temp is not equal to null because it is pointing to 1. And what is temp dot data? Yes, what is temp dot data? Temp dot data is 5 actually, which I am going to delete. But here, what is temp dot data? Here the temp dot data is 1, isn't it? So I will skip this step. I will move to the next part. Are you getting it or not? See, I am checking two things. Temp is not equal to null. Yes, temp is not equal to null. So it means temp is 1. What is the second part of the algorithm? Temp dot data is equivalent to key. The key is 5. Temp dot data should be 5, but it is not equal to. It is temp dot data is now 1. So it means this is not the node which I am going to read. So what will I do? I will go to the next node now, right? I will skip this step. Then I will traverse the list. I will loop till I will get temp dot data is equal to 5. So what will I do? I will set previous is equivalent to null now. This temp. Because see, initially I will check temp dot data equal to 5 no. Temp dot data equal to 5 no. Here temp dot data equal to 5. I will find it in the third step. So here what I will do for that, it is simple. I will simply check set previous is equal to null as per this statement. So what will I do? I will loop till temp not equal to null and temp dot data not equal to key, right? I will loop until then. Here also it is not null and not equal to key. Here also not equal to null and not equal to true. When I reach here, it becomes true. So at that time, what I will do? I will set previous is equivalent to temp, and previous, initially previous was what? See, when I move to the next step, if you say like initially previous was null, now previous it updates, it becomes previous is equivalent to temp. Or in other words, next time it becomes previous is equivalent to now 1, right? And the next time temp becomes temp dot next, isn't it? And next time temp is equivalent to next node, it is 3. Fine. Then in the second iteration, previous again becomes temp, and now previous becomes 3. See, in the next time, in the second iteration here, again previous becomes temp, and it is previous now becomes 3, right? And temp becomes temp dot next, same steps are same. And इसकी जो link है, what is the link? It is temp is equivalent to 5 now. See, now it matches the key. When it matches the key, what will happen? Loop exits, or I can say We'll stop. When loop exits, what happens? Because when loop exits, what does this mean? This simply means that temp dot data, here I will write, temp dot data becomes what? Yes, becomes key, or I can say 5, whatever was there, which I have to delete. Right? Then after that, I have to check, was the node found? Yes, node was found. So what I will do? Is temp now equal to null? No, temp is now equal to 5. If you check here, now temp is equivalent to 5 as per the algorithm. Here I am writing. So what will happen? We will continue. So after we continue, what we'll do? We'll delete the node. Because we'll go to the next step of the program. Right? Temp is equivalent to 5. Temp is not equal to null. We'll continue till we'll get temp dot data. So we have to do like this previous dot next, this one. We have to update it now. Previous dot next is equivalent to temp dot next. So with this step, the node will get removed. So it will be previous is now pointing to what? If I will write like this, let me choose here. Previous is now pointing what? Is now pointing to 3 because it was the previous, and temp is pointing to what? Temp is pointing to 5, isn't it? Then temp dot next is 7. Temp is pointing to 5, but temp dot next would be 7. If I write like this, temp dot next is simply what? It is now 7. So here temp dot next was temp, and temp was 5, and this temp when it was 5, so at the same time this is the key. So with this, previous was pointing to 3, temp is pointing to 5, and now temp dot next is pointing to 7. Right? So 3 dot next, if this is the node, now temp dot, if it is temp dot next, now the temp is pointing to 5. So it simply means that we are writing, if I will write a node 3 dot next, it is equivalent to what? It is equivalent to 7. So it means we are skipping 5. So this, with this way, 5 gets removed from the list. So the final list becomes, if I will write over here, the final list becomes like this. It is 1. Simply I will write 1, 3, and then it is 7. So with this way, we have removed the this node 5 from the linked list. Yes, we have to delete the node 5. So we are simply writing this node. We are setting in temp, then temp dot next. It is pointing to actually 5. So we are simply writing 3 dot next is now pointing to 7 instead of 5. So with this way, 5 is being removed. Fine. So this way we are actually deleting the element in a linked list. So we have removed this element following these steps using this algorithm. And I hope it is clear with the help of this algorithm. Right? Okay, so this was deletion. Now let us go further. Shall I delete this drawing, or you want to take a screenshot? You can take a screenshot of it if you want to explain, get things clear. Okay, I am deleting the drawing. Yes, now let us go to, yeah, today's topic would be now doubly linked list. Now what is a doubly linked list? Till now we were discussing singly linked list, right? Now what is a doubly linked list? It is simple. Again, it is a kind of a linked list. But previously we were discussing about nodes. Here the node would be like, let me bring this. See here. Let me write here. Hope it is visible. Screen. So it is a node. Till now that we discussed, the node was containing only what? Only two parts, isn't it? But in doubly linked list, the node is having three parts, right? Later I will draw the arrows. Okay. See here, a doubly linked list is a type of a linked list where each node contains. Actually, it has got three parts: data part, next part, and previous part. So it is the data part, the middle one. It is data part here, I can say. And I have left and I have next, or I can say previous. See here, it is left and right. This pointer reference to the next node. So it is a pointer that is referencing to the next node. We called as it as next, or here also it is written as next, right? And this part, it is called as a previous part, or I can say reference to the previous node. Like next was referencing to the next node, and this previous is referencing to the previous node. So it is called as simply previous, right? So actually node has got now three parts: data part, left part, and right part. Left means previous reference, right means next reference, right? So with this way we can say that this previously the singly linked list, in that the traversal was in only one direction, but here the traversal is bidirectional, means we can traverse the linked list both forward direction as well as in backward direction. So with this type of linked list allows traversal in both directions, both forward as well as backward. So this is the basic linked list, doubly linked list. Three parts: data part, previous part, next part. Previous is referencing to the previous node, next is referencing to the next node, right? We can traverse, or I can say this doubly linked list allows the traversal in both directions, both forward as well as backward. Right now, see, this is the practical example of doubly linked list. Can anyone explain how is this a practical example of doubly linked list? Yes. Okay. It will insert and delete in both hands. Yes. Okay. So if we see the practical example, it is simply now web browsing. Whenever we are browsing the web, so it is a doubly linked list because you can If you have visited so many websites, so many web pages, so you can use those arrows, back arrow and front arrow. Front arrow is simply referencing to the next new page. Back arrow is referencing to the previous page. So we are at some point, data point. So you can go whatever page you are viewing. That is like suppose data. So if you want to go to the next page, so simply click on the forward arrow, or you can go to the page that you already exited. You can go to the click on the backward arrow and you can go to that page. So simply we can go back and forth using those arrows, forward arrow and back in file systems as well. Whenever you are searching for a file, right? So whenever you are opening file, folder, subfolder, etc., etc. So you can toggle between these files by switching forward and backward. So that is a kind of a doubly linked list, because here also you have got two arrows, forward arrow and backward arrow. So it means we can toggle between back and forth. So that is also a doubly linked list. Here also, if we see the example over here, see here. If we check the examples, I have got 3 pages: google.com, Wikipedia, and openai.com, right? So when I hit the back button, what will happen? You go to the previous page, like suppose google.com. When you hit the forward button, you go to the next page, like suppose openai.com. So with this, you can toggle in between, like suppose it is null, nothing is there. Then you click it on google.com. So you went from null to google.com. Then if you click on the next, you will go to wikipedia.org. When you click on the previous, you will go back to Google. Similarly, when you click on next, you will go to Wikipedia. Then again next, you will go to OpenAI. If you go to previous, then you will go to Wiki, and so on. So this is actually how these doubly linked lists are working. So this is the practical example of doubly linked list. Means how do we view pages in a web browser? Viewing of, or I can say visiting different pages in a web browser is a practical example of doubly linked list. I guess it is clear. Then we will do it as operations. Yes or no? Yes. Yes, tell me. Is it clear? Great. Any other example you know about this, where you can relate this doubly linked list? Yes. See here, I don't know whether you are whether my editor is like you are viewing my this na editing tool, annotation tool, or any editor where there is an option of undo and redo, right? So that undo redo is also doubly linked list. When you are undoing, it means you are going previous. When you are redoing, you are going to the next. So that undo redo is also a kind of an application of this, or I can say live practical example of this doubly linked list, right? There is one more example, this now of in a media player. If you have got so many songs in your playlist, so you can click on next or you can click on previous. We are getting that now. Whenever we are playing a song, right? So what does this mean? We have got that interface. There is an option of previous, next, and play. So that previous means we are referencing to the previous node. Next means we are going to the next node, or I can say next song. So that is also practical implication of doubly linked list, right? Or even these. Yesterday I told you about that those train coaches. That is also doubly linked list, because those coaches, they can be linked together in both directions. There is no, I guess, front and back in those coaches. They're not designated like that way. This is the front of the coach, this is the back of the coach. It depends how you connect it. So you can connect it both ways, right? Because they are linked together, na, those coaches. They are linked together in both directions. So we can go from one coach to the next or that coach to the previous coach. So that is also a practical example where doubly linked lists are there. You can go from the same coach to next coach or that coach to the previous one. Because based on that coach, you will be knowing which is after it and which is before it. Right. So these are some of the applications of doubly linked list, or I can say relate this to the practical scenarios where this actually is. Because once you relate these things now, only then things are becoming more clear. I hope it is clear now. Yes or no? Do confirm. Yes, is it fine? Then we'll go to the operations. If it is clear, just type your message. Yeah, slideshow is also, see here, if I'm going back and forth, good example you are giving. Like see, I am pressing the next. So you will see the next slide. Next. I am pressing the back. This is back and forth, previous and next. So this is also a good example of doubly linked list. Nice. Okay, good. So this was a theoretical concept about doubly linked list. Now let us go to it is programming part, or I can say the algorithmic part. See, now I have to insert an element into a doubly linked list now. Right? See here again. Let me keep this window over here. Okay. So I have the input. Same in the previous case. I was having a linked list as input. Then I am inserting a new node to it. So the value of to the insert would be like this. The value to insert into a new node. And what would be the output? The output would be simply doubly linked list with a new node added at the end. Right? Can anyone tell me what will happen? What are the things that would change? Or how these things will happen? Yes. Yeah. Can anyone tell me? Okay, it will create a new node, assign data for it, and assign previous. Good. Need to save address of the next and previous entry. Very nice. Fine. Okay, let us explain it. See here. Firstly, what we have to do? We have to create a new node. And you know how do we create a new node, isn't it? Last time also, we created a new node in a singly linked list. But their creation was simple. There were only two things. One was the data, another one was the reference or a link or next, we call that as. But here we have three things: previous, data, and next. Right? So here, if we see set new node dot data, set new node dot next, and set new node dot null. So we have to designate what? Three things over here. Fine. As we know, because we have got three things. Right? Just a minute. Okay. So simply we are creating three things, right? Actually, we are creating only one node, but that node contains three things. And they are like data, next, and previous. Right? So then we are setting, yeah, new node dot data is equivalent to data means assign whatever data we have got, input data. We'll assign that input data to new nodes. Like suppose if I have this, I am creating this node, and you know this node has got three parts: data part, previous part, and next part. So I am assigning data to this part. Then simply set new node dot next is equivalent to null. So simply means this node will be the end. If I will set this node as null. So what does this mean? This means it would be the last node, right? Or I can say the end of the doubly linked list, because the next pointer is null, right? If I will set new node dot previous is equal to null. So what does that mean? New node dot previous is equal to null. It simply means we are initializing this previous node to null. So when both next as well as previous are null. So what does that mean? Yeah. What does that mean? Means this is the only node. Initially the list was empty. So whenever I am initializing this previous to null, right? So it means the previous as well as next is null. So it is the only node. But we'll discuss this later, whether if only this previous is null and it is not null, this one. So it cannot be the only node. Now what if the list is empty? I have to check that after creating the node here. Check if the list is empty. For that I have to set head is equivalent to new node. Fine, if list is empty. So what does this mean? This simply means that the list has no nodes, right? Then we'll return, because list has no nodes, so simply we'll return. Else if the list is not empty, what we'll do? We'll do these steps. Set temp is equivalent to head. What does that mean? Set temp is equivalent to head. Yes. So we'll simply refer our head node to temp node. Right? No, first is this: set head is equivalent to new node. If list is empty means that head is equal to null. So for that we'll simply write if empty we'll make new node as head. with this statement. Again, I am repeating it. I actually skipped one step. See, I will start from here. If list is empty, that means head is equivalent to null. When head is equal to null, so what does this mean? We'll check if list has no node. Simple. When head is equal to null, it means the list has no nodes. Then we will set what? We will set head is equivalent to new node. If there are no nodes, then we will set this head equal to new node, right? If it is empty, we will make new node the head of the list. Simply, when the list is empty, we will make this new node as the head of the list. So that would be the only node of our linked list, and we will return. Then if this is not the case, means if this is not true, so what will happen? Then we have to check, means if the list is not empty. Now we have to follow these steps. For this, I have checked if list is empty, we have set new head is equivalent to new node. But what if head is not equal to null? Then I have to set what? Temp is equivalent to head. So we will simply start traversal from the head node. We'll start traversal from the starting node, right? We'll start, then we'll start. So initially I have checked if list is empty, so we'll make head as a new node because we are inserting a new node. So if that is not the case, we'll start traversal, right? So we'll loop until we reach the last node, means temp dot next is not equal to null. We will loop till what point? Till we will reach temp dot equal to is not equal to, means whenever this is temp, this is not null, temp dot next not equal to null, temp dot text not equal to null, here temp dot text not equal to null, and if it is equal to null, so what does this mean? It means we have reached the end of the list. Then we will set temp is equivalent to temp dot next, right? So we'll set temp dot next, means we will move forward to the next node. We will set temp is equivalent to temp dot next, means we will move to the last node, and set temp dot next is equivalent to new node. Simply we will set temp, whatever was this, we'll set it to temp dot next, means we are out to the last node, and this temp dot next, it would be this new node that I have created over here, and this new node dot previous, it would be now this temp for which I have set the next equal to new node, and then we will return. So this is how do we insert a new node in a doubly linked list. So it is simple, not that simple like it was in previous case, but not that difficult. Okay, let me take an example of it to make it better. For example, I have nodes 10. I will be using back and forth links like this. So it means both previous and back. Otherwise, okay. Let me write like this: 10, 20, and 30. These are the three nodes, right? This is next, this is previous, this is next, and this is previous, right? Here head is 10. Let us do it with example, right? Now I want to insert another node, like suppose 40 at the end. So new node is equivalent to 40. Let me write here. New node is equivalent to 40. Fine. Yeah. Next is equivalent to null. I have to check. New node is equal to 40. next is equivalent to null, and I will also write previous is also equal to null. Right? Now I have to traverse until what? Until I will reach the last node, means until I will reach this 30. Temp is equal to 30 means this is the last node. So what I will do? I will write like 30 dot next. After doing this now, see 10, I will traverse till 30 dot next is equivalent to 40. I have to update it. So temp is equivalent to initially 10. Now temp is equivalent to 20. And now temp is equivalent to 30. When I found temp is equivalent to 30, so I will update. I will simply update 30 dot, like suppose next. It should be 40. And what is 40 dot previous? Can anyone tell me what could be the 40 dot previous value? Yes. Yeah, it would be simply the last node, that is 30. So finally, if I check, it would be 30, 10, 20, 30, and 40. So with this way, I am actually inserting a new node in a doubly linked list. So these are only two things that I have to keep in mind. I have to make a loop till I will find temp is equal to 30. When I found temp is equal to 30, it means it is the last node. So once I found it is the last node, then I have to update. Update means 30 dot next will be 40 and 40 dot previous would be 30. So with this way, this will become the last node of the linked list. Right? Hope it is clear. Simple. Hai. Only keep track of these two variables. Yes, is it fine? Then we'll go for a break. After that, we'll see, I guess, deletion or insertion in between. That was at the end. Simply, we are going for the next. If it is like null or if it is the last element, we will make the new element as a next of this element and a and previous of the new element as the last element. Okay, fine. If it is clear, just type your message, yes or no. Okay, let us go for a break. We will be back at 20 what? 2010. Oh, 10 is there. 2020. 2020 is fine. Okay, till then, take a rest, take a break. Okay, sorry, it should have gone to everyone. It went to somebody else. Okay, welcome back. Hope you all are here. Yes. I hope you all are back. Yeah. So this was the algorithm that we discussed, right? Okay, shall we continue? Okay, fine. See, this was the algorithm that we discussed. We are giving input, the value which we want to insert into the new node. Then we will get a doubly linked list with a new node added at the end. So for that, these are the three things. We are creating a node with this data, null and null. Then we are checking if the list is empty, means when head is equivalent to null, when head is pointing to null. So simply when head is pointing to null, it means when you have got a this train engine, but thread is pointing to null, means there is no coach attached to it. So that means that there are no coaches, so the list is empty. There is no train attached, there is no coach attached to it. That means that is simple. Yeah. Am I audible? Okay, who is this saying that your voice is not audible? Okay, fine. So I was just saying that if you have only DMU, train engine, but no coach is attached to it, what does this mean? It means head is equivalent to null. When head is null, it means the list is empty. Right? So at that time, we say head is equivalent to new node. Means whatever coach you want to add to this list, you will simply get that coach and attach it to the head. So simply head is equivalent to new node. Simple. Then return. Else, if now there are some coaches attached to the DMO, so we have to check. Set temp is equivalent to head. We will simply assign a variable. We will attach our head to that temp variable. Then we will set while temp not temp dot next not equal to null. Then we will update this. Make use of loop in order to check for all the coaches which coach is not attached to null. When a coach is not attached to null, it means the coach is not last node. We will go to second coach. If it is attached to null, we mean it is the last coach, and we will traverse till we will reach to the last coach. It means when we reach to the last coach, it means that coach's next would be null, right? So for that purpose, we are just finding out that this coach is the last node, or I can say the last coach. So for when I have to add a new coach after that, so simply what I will do, I will set the till now the last coach is next is equivalent to new node, and new node's previous is equivalent to the last coach that was present in that train. So that is simply how do we insert a new node at the end of a doubly linked list. It is as simple as that. I have kept it. Okay. Yes, this is the program for it. Simple. Again, I will give a bit of explanation to it. Although it is self-explanatory, see, this is how do we create a node. Three parts: data part, next part, and previous part. Then this constructor, I am passing data into it. Data is D. In the next part, I am passing null, and in the previous part, I am passing null. So simply, I am simply creating a new node like this. This is a node that I have created. Here I have kept data, and it is also null. It is also null. So this is a blank node with this, not a blank node, a node with single node, data D and front and back, or I can say previous and next pointing to null. Now node head is equal unto null. So what does this mean? Empty list. वही तो मैंने बोला, if your DMO of the train is not attached to anything, so we'll say simply it is null. Since insert at end operation, create a new node that we created over here. Simply we'll call that method new node is equal to new node data. Now we'll check if list is empty. If head is null, again head is equal to new node. Simply if DMU is not connected to any coach, simply we'll attach a new coach to the DMU. So we'll attach this to head. It will become the only node in the list. My presentation is not visible. Is my presentation visible? Why are you then asking, distracting the session by you asking these? Okay. Yeah, now it is not. I actually tried to reshare it now, maybe because for some it might not be visible. That is why. Okay, I hope now it is visible again. Fine. Yes, so we are discussing this. So when DMU is empty, means it is not connected to any bookie, we will say that train, there is no coach attached to the DMU. This is the new, I can say coach, which I have created, or which I have, yes, which I have created, or I can say a node. Now I will check if it is empty. Simply when the DMU is not connected to anything, right? Then after that we will see. But if it is empty, simply then we will connect this new node, new coach that I have bought with the head. So it will become the only node of the linked list like this. With this step, simple. See how simple, easy it is. I have kept it very simple. Then I will traverse to the last node, because if it is the case when the list is empty, after that what I will do? If the list is not empty, it means there are so many nodes already there in the list, right? Then I have to traverse all the nodes till what? Till I will reach the last node. Fine. I have to traverse all the bookies, all the coaches, till I will reach the last node. So for that, I will write node temp is equivalent to head, while temp dot next is not equal to null. Again, I am creating a temp node head. Then it is incrementing to here. Then it becomes temp. Now it becomes temp. So till I will find that temp dot next is not equal to null. Till then I will traverse. Here they go. Temp dot next is not equal to null. Temp dot next is not equal to null. Here also temp dot next is not. But here temp dot next is null. So I will reach here the last node. Fine. After reaching here, link new node at the end. When I reach the last node, here I have to link it to the node that I have created. So for that, temp dot next state will become new node. Means this is now temp. Temp dot next state will simply become the new node that I have created. And this new node dot previous, it will become what? It will become the temp that was right now. So that is the only step. Temp dot next will become new node. New node dot previous will become temp. Here, check it. This was now current temp. I mean to say last node. This is the new node that I have created. So when I have to insert it at the last, I will simply write temp dot next, it will become new node, and new node dot previous, it will become the temp. So this is how do we link a new node to the previous node. So then I will print the list. That is a different thing. So this is the very basic algorithm for inserting in a doubly linked list, and you can remember it easily. because I have kept it very simple. I hope it is visible and it is clearly understood. Just give a thumbs up if you got it. If not, then tell me, I will repeat it again. It is not that difficult, I guess. It is very easy because I have kept it simple. Okay, this was simply what? This was inserting at the beginning. Sorry. Now what if we have to insert an element at the beginning? Again, simple. See here, input would be head pointer to the doubly linked list and data value to insert. Means we will be creating a node, right? And we will be inserting that node to the doubly linked list, but at the front. Means simple. Head will point to right. Head dot next would be this new node, right? We'll create a new node with given data. First step would be like this. Then we'll set new node dot previous at to null. See, head dot next would be new node. New node dot previous would be null. These are the only two things since it will be the first node. Set new node dot next to point up. New node dot next will point to what? It will point to the head, means current head, the first node which was initially. And previous of this step would be new node. See here. If the list is not empty, head is not null. That we are checking. Set head dot previous to point back to new node. Then head to new node would be simply this. So this is how do we insert a new node at the front. Got it? Yes or no? If we explain it in detail by giving an example. See, it is simply we have to insert a node at the beginning of the list like we did previously at the end of the list. So here we have to insert the node at the beginning of the list. If we check, there are some variables, or I can say the input given to this algorithm. Like we have head, isn't it? Head pointer to the doubly linked list. It will simply pointer, it will be a pointer to the current head of the list. Like if you have got this linked list, so there would be head and it would be a pointer, this head, to the current linked list, the linked list which we are having right now. Like this is the linked list with so many nodes. There would be data, means the data which you want to insert, or I can say a new node, right, which you want to insert. Anything like previously we deleted, we inserted, I guess 40 or something like that. So this is would be the data that we want to insert, like 10, 20, 40, etc. Then there would be output. Output would be simple. Already existing linked list with a new node at the beginning of it. Now let us explain it, this algorithm step by step. So initially what we are doing, we are creating a new node, isn't it? So the new node would be simply, I can say we'll create a new node with the given data. So what does this mean? We'll create a new node with the given data. This simply means I can say like na, it is if we explain it like this way, whenever we declare a variable, what does that mean? Previously I also told you, when we declare a variable, yes, when I write int a is equivalent to 3, what does that mean? When I am writing, for example, let me write here, int a is equivalent to, like, suppose 4. What does this mean? When I write int a is equivalent to 4, can anyone? It is simply, actually we are assigning a variable, means we are actually creating a memory location of 2 bytes. If int will let us suppose int will occupy 2 bytes of memory, so we are actually assigning or creating a memory space. Variable is actually a memory location, and that memory location is of 2 bytes, and we are assigning 4 to that memory location, isn't it? It is as simple as it. So similarly, when I am saying that I am creating a new node, it simply means memory is allocated for a new node. And after that, when I say new node data, right, like not previously when I was writing, so that is assigned the input data value. So when I say new node dot null, or new node dot I can say new node dot next and new node dot previous. So when I write new node dot previous is equivalent to null, so what does this mean? When I write this, new node dot previous is null, so what does this mean actually? So this simply means that the new node will be the first node, because it would be new node dot previous, the new node which I am creating. If it is previous is actually what? Null. So what does that mean? That means it would be a first node, because it is previous link. It is referencing to null, so it would be the first node, right? So when I write new node dot next, so if it will point to what? Head. So what does that mean? If it will point to current head, not head, head is here. Now we are actually using a for loop, and we are actually using this current head for each loop in order to check this head dot next is equal to null for the last one. So I am just using this new node dot next to point to the current head. So with this, the next pointer of this new node is set to the current head. So it will simply do what? It will simply connect this new node to the existing list. As the list is not, if the list is not empty, it was simply, if the list is not empty, means head is not null. We have to check if this list, if the linked list has already some nodes, means that head is not equal to null. We are checking that head is not equal to null means what? The list is not empty. So after that, we will set simply head to new node. This set if list is not empty, we will set head is not equal to null, that I have checked. We will then set head dot previous to point blank to new node. So it means head dot previous. What head dot previous means? It will point back to new node, means I have this node, and now head dot previous, head is this. When I say head dot previous is this node, so it means it will get inserted at the thread and set head to new node. Now the previous head, it will be a new node, right? Then we will update the head. For example, let us take the example in the like the previous case. Let me make it clear. Like suppose I have a linked list with some entries. Like for example, I have a list with 10, 20, 30. This is like next, it is previous, this is next, and it is previous. So I want to insert a node like suppose 2 or 5 at the beginning. Right? So new node would be, what would be a new node? If I will write like 5 or 2. So new node would be, I will say like 5. So I have to insert it. So previous would be iska previous. Let me write here. Because for a new node there would be data previous and next. It is previous would be what? Simply null. And next would be what? 10. So this is this na when I will insert it. As we know, the list is not empty because there are some items in the list. So what will happen? You know, there are 3 already existing nodes in the list, and head is 10. Head is also not null. Then I will update what? I have to update 10 dot previous. To what value I have to update 10 dot previous? See, 10 is this head is equal to null. Head is equal to 10, not equal to null. Now what would be 10 dot previous? Can anyone? What would be 10 dot previous? Yeah, it would be equal to 5. 10 dot previous would be equal to 5. And what would be new head? What would be new head? New head also would be 5. Simple. Yes, new head would be also 5. And what would be the final list? What would be the final list now? It will be simply, yes, 5, 10, 20, 30. It would be like 5, 10, 20, and 30. So this is the new node that we will be getting after inserting the node at first location. I hope it is clear. Yes. Yes, it is. Is it clear? Okay, now I guess at the start of the session, today's session, we discuss about deletion algorithm. Can anyone tell me what is the delete complexity of deleting an element in a singly linked list? If I will say deleting a node, given it is pointer. Let me. If I will write deleting a node means where we already have some reference, means we already know, and it is not a last node. Means deleting a node with a, I can say, given pointer. So can anyone tell me what would be this complexity? Good. Its complexity would be order of 1. right? Because it only requires the pointer assignment. And what would be the complexity of deleting a node if it is the last node? Yeah, what would be the complexity if it is the last node? Yeah, it would be big O of n, because can anyone tell me how? Can anyone tell me how? How it is big O of n? Number of iterations because of traversion. Good. Because here, whenever you have to delete a last node, you have to check for that, right? So you have to traverse the list. You have to find the low node. So there would be order of n time to find the node before the last node. And there would be, for updation, it will require only order of 1 time. But whenever you have to delete a node at the last, so you have to traverse the node. You have to find the node. So for that purpose, we are just saying that its complexity is order of 1. And still, if the element is not found in the list, like suppose unsuccessful search, at that time also it would be order of n. Yeah, what would be the complexity when we say of insertion in a doubly linked list? Yes. Big O of 1, worst case order of n, big O of 1, big O of 1. Can you justify? Can you justify your answers? Yes. See, it is complexity actually depends upon the position where we are inserting. Like suppose in previous case, in deletion, we said where to delete a node. If we have to delete a node in a given with a given pointer, means we already know the reference. So at that time, it is simply go there and delete it. But if it is at the end, we have to check for the node. We have to traverse the list. So at that time, we say it is order of n. Similarly, when we take the case of insertion, so it depends on the position where we are actually inserting. For example, if we are simply inserting at the head, so at that time it would be simple. It would be order of 1. Just update the new node. Right? When you are inserting at the head, what do you have to do? Just go there, update the head. Make head of next is equal to new node and new node of previous is equivalent to what? Null. That is it. So it would be a constant time operation. Are you getting it or not? Tell me. So it would be simple when you are inserting at the front, at the head. So only thing is we have to update the head. Head of next is equal to new node of previous is equivalent to null. So that is it. It is order of 1. When we have to insert at the tail, so what we have to do? See here, two things are there. If you maintain a pointer, means you know the reference, right? At that time, it would be only 1. Because at that time, what we have to do? You have to just update the new node's pointer and the tail pointer. But if you maintain a tail pointer, then at that time also it would be a constant time. So what if you have to insert at a specific position and you don't have maintained any tail pointer or any kind of a pointer? Means you have to insert after a node or before a particular node. For the node you don't have a direct access to, but if you have direct access to the tail node, at that time it have only one constant time. But you don't have a direct access to a particular node and you want to insert a node before some node and after some node. So what would be the complexity? Yes, tell me, what is the complexity? Yeah, anyone? Simple, based on the position. Good. So I am just saying you have to insert it after a particular node or before some particular node, means in between, and we don't know that, we don't have the direct access to the position. What would be the complexity at that time? Simple, it would be order of n. Why? Because you have to traverse to that desired position after some node and before some particular node. So it would be of the order of n. Getting it? So whenever you want to insert a node before a particular node or after a particular node, so at that time the complexity is order of n, because we don't have a we don't have any kind of a pointer that we are saying, right? Any kind of a pointer that have a direct access to it. So for that purpose we are just saying that it is complexity would be order of n, because the time we require a time to traverse to that desired position. Right? Okay, so I guess we discussed all these things. If you have any questions, you can ask. Tomorrow we'll start with the deletion and circular key, then we'll go to stack and queue. After that, we'll start with nonlinear data structure, that is trees and graphs. And we'll do all the algorithms of trees and graphs. Linked list is a bit kind of this now, not tedious I can say, but it involves more these logical kind of things. Tree is easy, stack is easy, graph is easy, queue is also easy, and that trees and graphs is much more important, because everywhere you will find those examples. Okay, any questions? Then we'll wind up the session. Because if we start a new topic, that will take not less than 20 minutes. Otherwise, I was about to start deletion and this circular queue. Any questions?
Okay, sir, we'll wind up for the day. We'll meet again by tomorrow at 7 p.m. Yeah, thank you, sir. Thank you so much.
Thank you, guys. Good night. Bye-bye. Take care.
Yeah, thank you, students. Good night. We'll meet again by tomorrow at 7 p.m. Thank you all for joining.